who knew that a simple plate of spaghetti could hold the secrets to the universe? This humble dish, often enjoyed in the comfort of our homes, has a hidden complexity that has captivated the minds of scientists for generations. We delve into the surprising world of spaghetti science, where physicists and researchers explore the fascinating properties of this everyday pasta. It's not just about cooking, it's about understanding the fundamental principles that govern our world. From slurping physics to ultra-thin strands, spaghetti offers a unique lens through which to understand complex scientific principles. The way it bends, breaks, and even the sound it makes while being slurped can reveal insights into material science and fluid dynamics. For nearly a century, scientists have been intrigued by the seemingly mundane spaghetti. Early experiments in makeshift outdoor labs laid the groundwork for what would become a fascinating field of study. Its simplicity, made from basic ingredients like flour and water, makes it an accessible and relatable model for scientific exploration. The transformation from raw ingredients to a cooked dish mirrors many natural processes, making it a perfect subject for study. The low cost of spaghetti allows for extensive experimentation, while its familiarity engages both scientists and the public alike. It's a bridge between the complex world of science and everyday life, making it a powerful educational tool. Spaghetti's journey from plate to laboratory began with a simple question: why does dry spaghetti always break into three pieces? This question, seemingly trivial, opened up a Pandora's box of scientific inquiry. This culinary conundrum, posed by the renowned physicist Richard Feynman, sparked decades of research and led to groundbreaking discoveries about the physics of brittle rods. His curiosity turned a kitchen mystery into a scientific quest, inspiring countless studies and experiments. Imagine spaghetti strands so thin they are nearly invisible to the naked eye. Researchers at University College London have achieved just that, creating spaghetti with a diameter of a mere 1/10 of a millimeter using a technique called electrospinning. These ultra-thin strands hold immense potential in various fields, including medicine and materials science. The incredible thinness of these spaghetti-like fibers makes them ideal for applications requiring biodegradability and nanoscale precision. For instance, they could be used to develop biodegradable scaffolds for tissue engineering, or as carriers for targeted drug delivery. Their small size allows them to interact with cells and tissues at a molecular level, opening up new possibilities for regenerative medicine and nanotechnology. Ever wondered about the physics behind a perfectly slurped spaghetti strand? Or why spaghetti sauce has a knack for splattering? Scientists have dedicated significant research to unraveling the mechanics of eating spaghetti, exploring the forces, fluids, and even the role of saliva in this everyday act. The act of slurping spaghetti involves a complex interplay of suction, capillary action, and the elasticity of the noodles. As we slurp, we create a pressure difference that draws the spaghetti upwards, while saliva helps lubricate the strands and facilitates their movement. The physics of spaghetti breaking, on the other hand, involves concepts like tensile strength, fracture mechanics, and the propagation of shock waves. Section 4. Feynman's culinary conundrum. Richard Feynman, a Nobel laureate known for his playful approach to science, was once puzzled by a seemingly simple observation: dry spaghetti, when bent, almost always breaks into three pieces. This became known as Feynman's spaghetti problem, and it sparked a wave of research into the fracture mechanics of brittle rods. The key to understanding this phenomenon lies in the concept of snapback and the propagation of energy waves. When a dry spaghetti strand is bent, it stores elastic energy. Upon reaching its breaking point, the strand snaps back, sending a shockwave along its length. This shockwave can cause secondary breaks, leading to the characteristic three-piece fracture. Section 5. Unraveling the secrets of cooked spaghetti. Cooked spaghetti, unlike its dry counterpart, exhibits a fascinating property called viscoelasticity. This means it behaves both like a viscous fluid and an elastic solid, responding uniquely to stress and strain. This unique characteristic is responsible for the way cooked spaghetti coils and knots, as well as how it absorbs water and retains its shape. The viscoelastic nature of cooked spaghetti arises from the interaction between its starch molecules and the surrounding water. As spaghetti cooks, water penetrates its outer layers, causing the starch molecules to swell and form a gel-like network. This network gives cooked spaghetti its elasticity, allowing it to stretch and deform under stress. Section 6. Cacio e pepe, a cosmic connection. Even a simple dish like cacio e pepe, a classic Roman pasta with cheese and pepper, holds surprising scientific depth. This dish, beloved by many for its simplicity and rich flavor, is more than just a culinary delight. It serves as a gateway to understanding complex scientific phenomena. Italian physicists have investigated the mozzarella phase, the clumping phenomenon that occurs when cheese melts into the pasta water. This phase is not just a culinary curiosity, but a subject of scientific inquiry, revealing the intricate dance of molecules. This seemingly mundane observation has unexpected connections to broader scientific concepts, including the origin of life. The way cheese and pasta interact can mirror the processes that might have occurred in the primordial soup of early Earth. The clumping in cacio e pepe arises from the interaction between proteins in the cheese and lipids released during heating. This interaction is a small-scale example of phase separation, a fundamental process in both cooking and biology. These molecules attract each other, forming larger and larger clumps. This self-assembly is a key principle in many natural processes, from the formation of cellular structures to the creation of complex organisms. Interestingly, similar phase separation processes are thought to have played a role in the formation of the first cells on Earth, where molecules self-assembled into organized structures. This connection between a simple pasta dish and the origins of life highlights the profound interconnectedness of nature and science. Section 7. From Plate to Paradigm, the Power of Simple Science. From the tiniest spaghetti strands glistening in the sunlight to the physics of slurping, which can be both amusing and enlightening, the world of spaghetti science exemplifies the power of using simple models to understand complex phenomena. It shows how everyday objects can be gateways to profound scientific insights. By studying the familiar and the everyday, like a simple plate of spaghetti, scientists can uncover fundamental principles that govern the natural world. These principles can range from the way materials behave under different conditions to the intricate processes that might explain the origins of life itself. Spaghetti science serves as a reminder that scientific inquiry can be found in the most unexpected places. It encourages curiosity and a sense of wonder. It encourages us to look beyond the surface, to question the ordinary, and to find joy in the interconnectedness of the world around us. So the next time you enjoy a plate of spaghetti, whether at a picnic or a family dinner, take a moment to appreciate the hidden science behind this culinary delight. Reflect on how something so simple can connect us to the broader mysteries of the universe. In every strand there is a story, a lesson, and a glimpse into the wonders of science. Take a moment to savor not just the taste, but the incredible journey of discovery it represents.